Okay, I'm trying to curate a whole bunch of these pre-response questions for you guys so that you can use them for your reviews for this weird modified BC Calc exam. All right, so in your graph here, you have two rates of flow, one called A of t and the other one called B of t. One's the rate flowing into tank A. One is the rate flowing tank B from 0 to 4.5 hours. All right, so the first one says how much water will flow into tank A. Will be in tank A at 4.5, and it says that both tanks start off as being empty. So the amount of water that's going to be in tank A at time 4.5 will simply be the integral from 0 to 4.5 of 2t minus 5 plus 5 e to the 2 sine t dt. I threw this into the calculator and it came out as approximately 66.532 liters. Okay, so part B says I have this interval from 0 to k. I want to know k is when the two values cross the first time. I want to know what is the difference between the amount of water in the tanks at time k. So the first thing we literally have to do is find time k. So we know that the B curve here is a constant 20.5, right? And that this is intersecting the A curve, which is 2t minus 5 plus 5e to the 2 sine t. So what I did is I put this in for y2. I have this already in for y1 and saw where they intersect. And the first time that they intersect is at 0.892040. Okay. Sorry about that. All right, so now what I need is the difference between the amount of water that's in there at time k. So the amount of water that's in the first one at time k is going to be 0 to 0.892040 of 20.5, right? The amount of water that's in the second one is 0 to 0.892040 of 2t minus 5 plus 5e to the 2 sine t dt, which when you throw this into the calculator, you're going to get 10.599 liters is the difference between the two tanks. Okay, so let's do part C. The area of the region bounded by the graph y equals AT and y equals AB from K to 2.416 is 14.470. How much water is in tank B at time t being 2.416? Okay, so the total amount of water that's going to be in tank B is going to be 0 to 2.416 of B of t dt. Okay, now we know that from 0 to 0.892040, we have a constant rate of 20.5 dt. So it's that plus everything from 0.892040 to 2.416 BOT dt. All right. So next move here is that we can recognize that this second part here is the part under the A curve minus the part between the two curves. So this part stays the same. But this is the value under the A curve. Two sine t. And this is the value of the area between the curves. So the difference between these would be the area below the B curve. So once you take all of that, push it together, you're going to get 48.313 liters, which is the amount that is in the B tank at time 2.416. All right, so let's look at part D of this problem. All right, so I'm given that from 2.7 to 4.5, water flows into the tank modeled by this rate W. And we want to know if the difference between W and A is increasing or decreasing at time 3.5. So literally, we need to look at the derivative with respect to t of W, which is this 21 minus 30t over t minus 8 squared minus 2t minus 5 plus 5e to the 2 sine t. And I want that evaluated at t equals 3.5. So you throw that into the calculator and you're going to get negative 1.143, which is clearly less than 0, which means the difference between these two things is decreasing at t equals 3.5. And that's the whole problem number 1. All right, so let's look at number 2. All right, so in problem number 2, they give me that f is this graph up here, and that g is the integral function from 1 to x of f of t. So we want the average rate of change for g from -5 to 5. All right, so if I'm looking at this problem, average rate of change is equal to g at 5 minus g at -5 over 5 minus -5. Okay, so g at 5 is the integral from 1 to 5 of f of t dt. So this is the area under the curve, which is going to be a triangle with a base 2 and a height of 4, plus a rectangle that's 2 by 4, which works out to be 12. G of -5 is the integral from 1 to -5 of f of t dt, which is the same as negative integral from -5 to 1 of f of t dt, which is going to be negative And then there's a triangle below the line, quarter circle, and then another triangle. And when I simplify that all out, I end up with 7 plus pi. So the average rate of change is going to be g of 5, which is 12, minus 7 plus pi, all over 10, which is 5 minus pi over 10. And that's your answer for part A. Let's look at part B. Okay, part B is a pretty straightforward question. It says, what is the instantaneous rate of change of g with respect to x when x equals 3? So what I want here is g prime of 3. So note, by fundamental theorem of calculus, g prime of x is f of x. So g prime of 3 is going to be f of 3. And when you look at the graph, that's 4. So that's all of B. Part C of the problem wants to know on what intervals is g concave up. So keep in mind that we just said the g prime of x is f of x. So g double prime of x is going to be f prime of x. So this thing is going to be concave up when f is increasing. Well, if I look at my graph, f increases on -5 to -2 and 0 to 3. So g is concave up on -5 to -2 and 0 to 3. All right, so there we go. Let's look at part D. All right, so part D here says, what are the critical points between -5 and 5, not including -5 and 5, and then classify each critical point as being a local max, local min, or neither. All right, so literally here, I need to know where is g prime of x equal to 0. That happens when f of x is 0, so that's at x equals -2, and x equals 1. Those are my critical points. If I look at -2, on both sides of -2, f of x is less than 0 on both sides of x equals -2. So this is neither local max or minimum. However, there is a sign change at x equals 1. F of x is less than 0 on -2, 1, and f of x is greater than 0 on 1, 5. So this means I'm decreasing down to 1, and then I'm increasing, so this is going to be local min. All right, so that's it for problem 2. Let's keep rolling on here. All right, looking at problem number 3, you're given this table. It says first, find the midpoint Riemann sum with 3 intervals and use that to approximate f of 6. So remember that the integral from 0 to 6 of f prime of x dx is f of 6 minus f of 0. Okay, so we're going to approximate this with the Riemann sum. Each of the intervals is 2 wide. The midpoints are 3.5, 0.8, and 5.8. And we're told in the stem of the problem that f of 0 is in fact 20. So this side reduces to 20.2, which is going to give me 40.2 is f of 6. So that one's pretty straightforward. A little bit of fundamental theorem of calculus and a little bit of Riemann sums. So let's move on to part B. All right, part B says, could f of 6 be 70? Well, we're told in the stem of the problem that f prime of x is stuck clearly between 0 and 7. Okay, so, well, if I take the integral from 0 to 6 of 0 dx, that has to be less than or equal to the integral from 0 to 6 of f prime of x dx, which has to be less than or equal to the integral from 0 to 6 of 7 dx. Well, this is 0. This is going to be f of 6 minus f of 0, and this is 6 times 7, which is 42. But we know that f of 0 is 20, so this means that f of 6 has to be between 20 and 62, of which 70 is not. So f of 6 cannot be 70. All right, let's look at part C here. C says evaluate the integral from 4 to 2 of f double prime of x dx from, 2 to 4 f double prime of x dx. So this is going to be f prime of 4 minus f prime of 2. Those values are in the table. They are 1.7 and 2. So this answer is negative 0.3. So that's literally using the table in the fundamental theorem of calculus. Part D of this problem is finding a limit. If you're not thinking L'Hopital's rule on this, then I have not done my job. So the limit as x approaches 0 of f of x minus 20 e to the x over 0.5 f of x minus 10. Well, this is the same as f of 0 minus 20 e to the 0 over 0.5 times f of 0 minus 10. F of 0 is 20. E to the 0 is 1. Half of 20 is 10. Minus 10 gives me 0 over 0. So the conditions of L'Hopital's rule have been met. So applying L'Hopital's rule, I get the limit as x approaches 0 of f prime of x. The derivative of e to the x is still e to the x. That's going to be 20 e to the x over 0.5 f prime of x, and the 10 goes to 0. So f prime of 0 is 4 according to the table. E to the 0 is, so that's just going to be 20. And half of 4 is 2. So this is negative 16 over 2, which is negative 8 by L'Hopital's rule. So that completes problem number 3. All right, so problem number 4, it's a little bit truncated because the rest of the problem runs us off into stuff that is not relevant for this PC exam. So I'm just giving you the parts that are. Consider the differential equation. dy dx is negative 1 plus y squared over x. It wants to show that the second derivative is what's there. So d2y dx squared. Second derivative of that. Derivative of negative 1 is 0. So then we just use the quotient rule here. Low d high, dy dx, because this is implicit, minus high d low over low squared. We know that dy dx is this weird negative 1 plus y squared over x minus y squared over x squared. We distribute here. We're going to get negative 2xy. Distribute that over here, plus the x's cancel, so that's going to be 2y cubed minus y squared over x squared. And we do a little bit of rearranging by the commutative property. We get 2y cubed minus y squared minus 2xy over x squared. So that verifies the second derivative that we expect in this problem. Okay, so part 2 gives me the initial condition g of 4 is equal to 2, right? So that means when x is 4, y is 2. All right, so it says find the particular solution. Or let this be the particular solution. So we want to know if g has a relative minimum, maximum, or neither at x equals 4. Well, we need to investigate the first derivative when x equals 4 to see if it is a critical point. So when we do that, we go negative 1 plus, now we know that the y is 2 squared over x, which is 4, and that comes up as 0. So it is in fact a critical point. Now that I know that it's a critical point, I have to determine the concavity at that critical point. So I take the second derivative, which I had in part A, right? So I say 2 times y cubed minus y squared minus 2xy over x squared. So let's see, that's 16 minus 4 minus 16 over 16. Those fall out. This is going to give me negative 1/4, which is less than 0. So if I have a critical point with a concave down, this has to be a local maximum. All right, so there we go. That's problem number 4. Let's do number 5. All right, so number 5, we're evaluating the improper integral 3 to infinity 1 over x squared plus 9 dx. This is the limit as b approaches infinity of 3 to b 1 over x squared plus 9 dx. Now, this is some variation on 1 over 1 plus x squared. If you pull the 9 out of the bottom, you get 3 to b 1 over 9 divided by 9 is 1. X squared over 9 is x over 3 squared dx. So now I'm in the inverse tangent form. I have to do a u substitution for x over 3. du dx is 1/3, which means dx is 3 du. So let's see, I get the limit as b approaches infinity. Let me write it out. It's 1/9. But the 3 becomes a 1. This becomes b over 3. 1 over 1 plus u squared 3 du. The 3 and the 9 become a 1/3. So I end up with the limit as b approaches infinity of 1/3 the inverse tangent of u from 1 to b over 3. All right, so this is going to become the limit as b approaches infinity of 1/3 times the inverse tangent of b over 3 minus the inverse tangent of 1. So let's see, I get 1/3. As I go off to infinity, the inverse tangent goes to pi over 2. The inverse tangent of 1 is pi over 4. So this is 1/3 times pi over 4, which is pi over 12. All right, so that's part A. All right, so let's look at part B. Says determine whether this converges or diverges. State the conditions of the test used. Okay, so this is the integral test. We can look at Fn, and by examination we can see that it's continuous, it is decreasing, and it is always positive. So we meet on the interval 3 to infinity, so we meet the initial conditions that are required of the integral test. From part A, we have that the integral from 3 to infinity of f of x dx is non-infinite. This means that the sum from n equals 3 to infinity of f of n converges by the integral test. And that's the entirety of the problem. All right, so let's move on to part C. All right, so part C asks me to determine whether this converges absolutely, converges conditionally, or diverges. You can use the ratio test here. Take the limit as n approaches infinity. Now, we can ignore the alternator here, because when we take the absolute value, it's going to disappear. So the numerator here is n, plus 1 squared plus 9 over e to the n plus 1. And then we flip it over here, so we get e to the n over n squared plus 9. When I break this thing apart, I'm going to get the limit as n approaches infinity of n plus 1 squared plus 9 over n squared plus 9 times 1 over e. As this thing goes to infinity, I have an n squared over an n squared. That's going to 1 times 1 over e, so that gives me 1 over e, which is clearly less than 1. And ratio test gives us absolute convergence, so this one converges absolutely by ratio test. And that's part C and the entire set of problems. So hopefully this was helpful. Come with questions to the drop-in, drop me an email, whatever you need. I hope you're doing well, and we'll keep moving on toward this BC exam. Thank you.